Okay, this is the AQA required practical on investigating how the resistance of a wire varies with its length. Hopefully you can see we have got some equipment in front of us. I'm just going to talk you through it. We've built this beforehand, we've built the circuit already, but just to save a bit of time and to make it nice and clear, if I talk you through it, hopefully you can see the power supply just in this corner, and from the power supply we're using direct current, and we're coming out of the power supply following this lead round. We've just got a junction here, and then we've got a crocodile clip, and the crocodile clip is connected to a length of wire, and this length of wire is on a board, a piece of wood with a tape that's also got some centimetre measurements, so we can measure the length of the wire, but we'll come back to that in a second. So we go through the wire, the current goes through the wire, and then as we come off the wire, you might be able to see this junction here, and this wire goes all the way back to the power supply. So we've got all of these wires connected together in series, and what we need to do, we need to measure the current in this circuit. So to do that, we need to use an ammeter, and you should know that ammeters we always connect in series to read the current in the circuit. So I'm just going to break the circuit here and put an ammeter in. Okay, so maybe not, you'll be able to see the readings on there. If not, we'll write them down, so it doesn't matter. Then we've got a voltmeter. Now if I just bring this voltmeter in, hopefully you can see it. The voltmeter, we need to measure the potential difference across this little bit of wire, because the whole idea of this is to work out the resistance of this wire as we change its length, and to do that we need the current, and so now we need the potential difference measured in volts. Now to do that we need to connect the voltmeter in parallel. So if I just lift that up slightly, you will see that this voltmeter is now in parallel, a bit further down, so you can see it. And this, when we turn the circuit on, this will give us the readings of potential difference between these 2 points, and this will give us the current in the circuit. Okay, so it's a really easy, straightforward circuit. So all we've got to do is decide on some length. So I've got this set up at 10 centimetres, and if we increase this from 10 centimetres, another 10 centimetres to 20, 30, 40, all the way up to 50, and each time we're going to write down on this results table here, we're going to write down our length of wire, what the potential difference was, what the current was, and then afterwards, when we do the calculations, we're going to work out the resistance from the potential difference and current. Okay, so first of all we'll just turn it on. Now obviously you won't see anything different, but you might see, hopefully you'll be able to read the readings that are on the ammeter and the voltmeter. So for a length of wire of 10 centimetres, we have got a potential difference of 0.96 volts and a current of 2.90. Now what I'm going to do, you can see if this meeting fluctuates, if the meter reading fluctuates, we're going to kind of just average it out, and I think that's about 2.9. Okay, the next we're going to move to 20 centimetres. So I've increased the length of the wire to 20 centimetres, and you should be able to see my voltmeter has gone up to 1.23 volts, and my ammeter, the current is now 1.92. Okay, we're now going to increase the length of the wire from 20 centimetres to 30 centimetres, like that. And again, if I bring the voltmeter in, so the reading of potential difference is 1.37, and the current reading is 1.44. And we'll go up to 40 centimetres. If I just move that out of the way, and I'll actually bring that round so you can still see it. We have now got the potential difference has gone to 1.44, and the current has gone to 1.21 amps. And our final reading we'll do at 50 centimetres, and we have a potential difference of 1.5, and then we have a current of about 1.01 amps. Alright, so we've done 5 readings, and all we've got to do now is use the potential difference and the current to work out the resistance of this piece of wire.
Okay, so here's our data. Now we've got the length of the wire here, so we've done 10, 20, 30, 40, 50 centimetres of wire. Here are our potential differences. Here's the current that we've measured, and then we've calculated the resistance by doing the equation resistance is potential difference divided by current. So you'll see here in simple terms that as the length goes up, the resistance goes up. Okay, it wouldn't matter what values we'd used here for potential difference. We'd have got a different value for the current with a different potential difference, but the resistance would have stayed the same. Okay, here's our graph. So we've got length along the bottom, resistance up the side, and you'll notice there that not only is it going up, but it's going up in pretty much a proportional relationship. So as the length of the wire doubles, you can see we're going up about 0.33 for each extra 10 centimeters of wire. It is worth noticing here that it doesn't go quite to the origin like a proportional graph would. That's probably because of the connection resistances. So you've got a slight systematic error in this experiment due to the resistance of the crocodile clips that you're using to connect onto the wire, and possibly some of the leads as well. So we haven't got a zero resistance even when we had a zero length of wire.